So gravity, historically it started out with thinking about the Greeks. Gravity was the idea of some things like to fall to the ground. So some things had gravity, and other things didn't fall to the ground, or they had less gravity. There was actually a concept called levity, right? So like, if I stick something heavy on the water, it'll sink to the bottom, but something light had levity relative to the water, so it would float. And it wasn't very predictive. You'd have to know what every object was and whether it had gravity or levity. So heavy objects have gravity, which makes them fall, and light objects have levity, which makes them rise. Seriously. And this is what people thought for 2,000 years. Meanwhile, the astronomers that have been around even longer were measuring where planets were and how the sun moved across the sky. And they would set up observatories in stone that we still see today that reflect where the sun is on different days of the year and how it moves through the sky. So this effort of measuring things with the eye culminated with these two guys. So one is Tycho Brahe, who was a Danish astronomer who essentially was friends with the King of Denmark. So at that time, the King of Denmark decided to spend about 2% of the gross economy of Denmark on his observatory. I mean, that was a cushy operation. And he measured with very high precision where all the planets were every single day. And he hired this guy, Kepler, to figure it out. And Kepler, he had lots of issues, one of which was Brahe didn't actually want Kepler to figure anything out. He wanted to have the credit. So he never gave Kepler all the data. Eventually, this guy, Brahe, was a big partier. Maybe true, maybe not, but it's definitely interesting. I think he also had a fake nose at some point. But he's partying, and he really has to go to the bathroom, but he doesn't want to leave the party, and he holds it in and develops a bladder infection and dies, which was maybe lucky, because then, once Brahe was dead, Kepler went to Brahe's house to say to his wife, I need to pick up all of Brahe's data. And she gave it to him, right? Whereas Brahe wasn't giving him the data. Now, Kepler was a great mathematician, so he pored over all this planetary data, and he figured out some stuff about the planets, in fact, how they move. And this became the basis, the basic observation that Newton's theory of gravity ends up explaining and gave us a lot of trust. Now, Kepler had other issues, like, for example, his mother, like, Kepler's a smart guy. His mother was a smart woman, but, in that time, if you were a smart woman, you would get in trouble. And she was always being accused of being a witch. Now, Kepler was reasonably well connected, so he would get these messages. Mom, locked up, accused of being a witch, will be burnt in 2 months. And then Kepler would go across Europe and talk to the Duke, spring his mother out of jail, and then go back to work. And this happened twice. So you think you have your problems with your mother? I mean, think about this guy. But notwithstanding, he figured things out. So what Kepler discovered about the planets were the key to Newton understanding gravity. And there were 3 laws of planetary motion. And these were the 3 laws, which don't seem to say anything about gravity. One is that the planets go around the sun in a shape called an ellipse, which is just a squished circle. The planets sweep out equal areas at equal times. So when a planet is closer to the sun, it moves faster than when it's further away. So right now on Earth, we're moving faster than in July because we're closer to the sun. And the square of the period of a planet's orbit is proportional to the cube of its semi-major axis, which is what we did for Jupiter. Now, these Kepler laws of planetary motion were for the planets going around the sun, but then you look at Jupiter, and those moons do the same thing, right? So whatever's making the planets go around the sun is the same thing that's making the moons of Jupiter go around Jupiter. And what Newton realized is that whatever this was also the same thing that, there's this famous anecdote of the apple falling and Newton going, oh my gosh. But what Newton realized was the same force that pulls an apple to the ground, pulls the moon around the Earth, also has the planets orbit the sun, the moon of Jupiter orbit Jupiter. They all follow the same pattern. And by looking at this, he came up with 3 laws of motion and the universal law of gravitation. And these 3 laws of motion and this universal law of gravitation are mathematical statements about everything in the universe. So it wasn't like we had to keep a list of what things have levity, what things have gravity. These rules cover everything. Okay? And the 3 laws of motion are maybe somewhat counterintuitive from your everyday life. Every body or every object continues doing what it's doing, whether it's at rest or moving at a constant rate in a straight line, unless it is acted on by an external force. So what this says is, if I were to slide something, you can see it stops. And if you look at your everyday life, for the most part, things eventually stop moving. And unlike Aristotle, what Newton said was, once you start moving, you'll keep moving unless something makes you not move. Whereas in the past, like Aristotle would say, well, the natural state is not to be moving. You will have to keep exerting a force to keep moving. But what Newton said, well, there's a force that slows it down. It's just the friction across the table. And if you look out on the planets, right, they just keep moving. Because guess what? There isn't much friction out there, right? So the frictional part is completely negligible. And they just keep going round and round and round. And the stars keep moving around. And that's Newton's first law. The second law is a mathematical statement that says it relates how an object changes its motion compared to the force that you exert on it. And essentially it says force makes things accelerate. So acceleration is a change in the velocity. And we'll go through lots of examples of what's going on. And the key is the acceleration in an object times something called its mass is the force. So mass is how much an object is resistant to having its motion change. That's what mass is, right? So, and the last one is it sounds like something very Zen. For every action, there's an equal and opposite reaction. No. But all it means is if I push on you, you push back on me, basically. So it's hard because we don't have things like with wheels. We only have one thing with wheels. But the point is you can imagine how a rocket ship works, right? The rocket ship shoots stuff out one direction, it exerts a force on the exhaust, but that pushes the rocket ship up exhaust pushes back. If we had sort of two nice wheelie chairs, we could both sit on the chairs and we could push each other away. And I would push and the other person could push, but both would go apart from each other, right? Even if you don't do anything, if I push on you, I will go back away from you. And that's number 3. Now, one thing to keep in mind, if we were to do that, I could figure out how much your mass is relative to mine using equation 2. So maybe you don't want to do that with me, right? So if you want to find out if you weigh more than someone else, you can just go, I'm going to sit on a chair, you sit on a chair, you push each other away, and you see who goes faster. The one who goes faster is the one with the less mass, which is that equation, Newton's equation, saying that. Okay, so these 3 laws of motion, do they talk about, is it about lead, or is it about feathers, or is it about water? No, it's about everything. Everything in the universe follows these 3 rules. And these 3 rules work really well, and it took, I don't know, a while. Let's go back. It took about 200 years to start finding holes in what these are going on. And that underlying, you have quantum mechanics, where things don't exactly follow these rules, but they follow these rules on average, which is why they work so well for big things. So the second thing he came up with, he came up with a lot of stuff. So there were other things too, all sorts of mathematical things. He also came up with a lot of really crazy stuff. Like he was into alchemy and weird stuff too. He was also in charge of the mint of England at the time. And he also apparently was a real jerk, but there you go. But he came up with this universal law of gravitation. And that, again, it's not about the sun, it's not about a planet, it's about everything. Everything with mass attracts everything else that has mass. And he called this force of attraction gravity. The strength of the force is proportional to the product of their masses, and it goes down with the square of the distance between them. Now, why that special way of doing that? And then also, the other key thing about it is the force goes it's directed between me and the other object. It goes on a straight line between me and the other object. Now, those things, they're very mathematical, but he didn't just think about them out of thin air. So he could look at it, he could go, how fast does this apple fall on Earth? And he realized that the moon is falling a lot slower than the apple. But how much slower the moon is falling is related to the square of the distance. So the apple is away from the center of the Earth by the radius of the Earth. The moon is about, we had an example, is it 20 Earth radii away or is it 20 diameter away? I forget what the number is. But the moon is that much further. Let's say it's 20 radii away. The rate that the moon is falling in order to go around the Earth once a month is 400 times less. So we had this observation, so that's why he put the square of the distance. But he also had Kepler's laws. So using Kepler's law, the one with the orbit is an ellipse, he could prove that if orbits are ellipses, that's the law of gravity. He also could prove that if that's the law of gravity, the orbits are ellipses. And to prove that, he had to invent an entire new branch of mathematics, which has been the bane of students since then, called calculus. But then, since he was the only one who knew calculus at the time, other than this guy Leibniz, is he also had to translate those arguments into geometric arguments. So if you look in the books he wrote, the Principia, you'll see it both ways. Because in order to explain it to him, if you didn't, no one had calculus at the time, except him. So the point is the other fact of Kepler's laws, that p squared a cubed is also explained by this law of gravity. So even if the orbits were perfect circles, you could figure out the law of gravity by the fact that the period squared when it's the size of the circle cubed. And then there was the first of Kepler's laws, was it the first or the second? The second. Equal area and equal time, which seems like, well, what's that going to tell you? That tells me that the force of gravity operates on a line between me and the other object. That tells you the equal area and equal time. So I have another worksheet which I've not handed out, so I'm going to skip ahead a page, and we'll come back to the worksheet on Monday, right? Today's Friday. So if you write that out as an equation, it looks like this. So we have the two masses there. We have the distance between them squared, which I write as big R. I have a little r with a hat. That's telling me that it goes in the direction between me and you. That's what the little r with the hat means. That tells you what direction is. So that's important. Forces have a size and forces have a direction, just like velocity does. It has a size and a direction. And then there's a minus sign in front of it, which means that gravity pulls you together. It doesn't push you apart. Now, this universal law of gravity, it is universal. It is for everything out there. So it applies to everything. Now, in Newton's laws, we talked about acceleration. We talked about velocity and changing velocities. We also talked about things having direction as well as size. So one thing to keep in mind is we'll talk about things called scalar. Like in physics, speed is a scalar. It just really has an amplitude. How much? How fast are you going? 60 kilometers an hour. But velocity is a vector, which means it has a direction as well as a side. So if we want to think about our velocity, what velocity is your change in position divided by the change in time. So if I were 10 meters north of here, and then 2 seconds later I was 40 meters north of here, my velocity would be 40 minus 10, but in the north direction, divided by 2 seconds. So the velocity would be 15 meters per second going north. Now this is important because we have to keep that in mind. If we want to think about acceleration, that's your change in velocity. So here I'm accelerating from 10 meters per second to 40 meters per second. So I would get 15 meters per second squared north. That's the direction of the acceleration. But what this means is you're accelerating when you change your direction of motion as well. Right? So when the Earth goes around the sun, it goes about 30 kilometers per second all the time. Right? So where's the force? What's the force of the sun doing to the Earth if its speed is never changing? What do you think? You said that. I said there was gravity. It's a force. But the Earth is always going 30 kilometers per second. So what's happening?
Changes the direction. So
it's going in a circle. So it's changing its direction. So we'll figure out what sort of acceleration is required by you going in a circle. And that lets us figure out a whole lot about gravity. So we'll do that, I think, on Monday. So we just at the end of last class, we talked about if you're changing your direction, but your magnitude of your velocity is unchanging, even then you're accelerating. Now, the key with acceleration is if you are in an object that's accelerating, you can feel it. That's what you feel. When you're sitting in a plane and you're going 1,000 kilometers an hour, you don't feel that. But if that plane changes its velocity by maybe a few tenths of a meter per second, you're like, oh, you think you're going to crash. And that's the turbulence. It's literally the plane going like this, more or less. That's turbulence. It's going up and down like that at a fraction of a meter per second, but it's going forwards 10,000 times faster. But what you feel is that part. Okay? So acceleration, if you're wondering, is this object accelerating? Imagine yourself sitting on that object. Do you feel the acceleration? And that'll tell you, right? So if you're going around in a circle, like there's the funny rides at the amusement park where you can stick up on the wall, you know that you're accelerating. And you can feel it. So acceleration can be also a change in the direction of the velocity without a change in the magnitude. And this is an example. You're not going to do a question like this, but this gives you an idea. Like if I were to go from walking north at 10 meters per second, which would be really fast to walk, by the way. It's more like running. If I were going north at that rate and then east at that rate, and I make a circle to turn, it's sort of like 7 meters per second squared, southeast. So why is it southeast? Because I stopped moving north, right? So the south cancels out that northerly motion, and then I'm accelerating towards the east is my final direction. That's just to give you a sense. I'm not going to actually ask you to calculate accelerations like this without giving you a formula, right? So there is a formula that helps you calculate accelerations when you're going in a circle. So gravity, what it does, one way of looking at gravity, is it accelerates objects. And in fact, it accelerates all objects in a given part of space in exactly the same way. So whether it's my keys or my phone, I'm not going to drop my phone, I might drop my keys, or a feather, it accelerates in the exact same way. And at the surface of the Earth, the acceleration is about 10 meters per second squared. So what that means is if I start falling, if I jump off something, in 1 second, I'll be going 10 meters per second, which is pretty fast. You know, it's enough to get hurt badly. And then the next second, I'll be going 20 meters per second. And the next second, I'll be going 30 meters per second. And probably after about 3 seconds, I'm not going to go any faster because of just the friction with the air. Something like that. So, if you remember, the definition of force was your mass, or the mass of an object, times the acceleration. So when we're standing on the Earth, we call this force weight. The force of gravity we call weight. So, for example, if your mass is 60 kilos, then your weight is 60 times 10, which is the acceleration, 600 kilogram meters per second squared. We multiply them out, and we give this a special name. Forces, we call them in newtons, just so when we see newtons, you'll know what that is. So, for example, my mass is the same wherever I am. Right? My weight is different. For example, if I want to lose weight, all I have to do is this. I have no weight when I'm in the air, just that moment. Because the gravity is Now, why does that make sense? I'm being accelerated by gravity, but actually I feel no force. Because the only reason I feel the force of gravity here is because the Earth's holding me up. So you feel your weight on your feet, right? But that's the force pushing you up. Gravity is pulling you down. So, for example, if I were to go to a different planet, my weight would be different, although my mass would be exactly the same. Okay? So, really what you want to do is lose mass, right? If you are interested in weight loss, you're really wanting mass loss. Okay, so that's just to give you an idea of what we call weight, what we call mass. Mass, in some sense, is how much stuff makes up an object. But really, like if you really want to get a feeling for what mass is, it's when you try to accelerate it, how much force is required to reach a given acceleration is its mass. Okay? A second type of mass that turns out to be exactly the same as the first, numerically it's the same, is how much gravitational force I feel. My mass goes in that formula too. And it's the same number because every single object, as best we can measure, has the exact same acceleration due to gravity. So Newton proved, I mentioned this, if the force of attraction to the sun follows this universal law of gravitation, then the planets follow Kepler's laws. And he also proved the converse, that if the planets follow Kepler's laws, then the force of attraction follows the universal law of gravitation. Those two aren't the same statement. They both don't, like if the first is true, it doesn't mean the second is true. You have to prove them both. That's a logic thing. Like, if A, then B, doesn't mean if B, then A. Right? So he proved them both, which meant that the sun indeed has this force, where this 1 over r squared force. But beyond that, you have the story of the apple, right, falling. You have the satellites of Jupiter, the tides, the lifting of the ocean as the moon moves past. We're all explaining quite nicely with Newton's law of gravitation. And essentially, other than tiny little weird things that showed up 200 years later, Newton's law of gravitation explains all the motion in the solar system very accurately. Now, there's extra little bits that needed to be explained, and there are different ways of explaining them, it turns out. And we'll go through two examples. The current theory of gravity is general relativity that came out from Einstein, and it agrees with the predictions of Newtonian gravity in almost every situation. But it looks, the underlying idea of what's going on is quite a bit different, but the consequences are almost the same. So what I'd like to do is, we already had enough ingredients. We're going to we figured out what's the power coming from the sun. Remember the power? It was 4 times 10 to the big number, 33 minus 7, 26 watts. Do you remember that? That's the power. I'd like to figure out the mass of the sun. Like, how many kilograms is the sun? Is it 100 kilograms? Is it 1,000 kilograms? Or do you think it's a really big number? Do you think it's a big number? It's a big number of kilograms. So let's do it. Now, on the website, there's a video of me actually doing an experiment to figure this out. We use a similar formula, but in the video, what we figure out is what's the ratio of the mass of the Earth to the mass of the sun, if you watch this. And the ingredients for that is, I had my daughter swinging on a swing. And believe it or not, that was the measurement that he made. And knowing how far the sun is away and how long it takes the Earth to go around. What I'm doing here is a little bit different, but it's the same underlying idea. So the first thing is the Earth goes around the sun in a circle, and we talked about this. Even when you go in a circle, you're accelerating. And there's a formula for that acceleration, which is how fast you're going in the circle squared divided by the radius of the circle. Right, and you guys probably have experienced this. If you're driving your car and you pull the turn tight, swing the wheel really hard, that will make R small, and everyone will slam to the side of the car. And if you are going the same speed, but you make a gradual turn, people don't feel, they don't get jostled so much in the car. Is that right? I think that's right, you know that. And you might not have realized it goes as velocity squared, but it does. So the acceleration for going in a circle is velocity squared divided by radius. We know the velocity. What's the velocity of the Earth? It's 30 kilometers per second. What's the radius of the circle? You can give it to me like in kilometers, or you can give it to me in terms of what we defined it, the number, like a unit. It even has the word unit in it. It's 1 astronomical unit. That would be right. Okay. The astronomical unit is the distance between Earth and the sun. So we can figure out, we know the velocity, is 1 AU, right? Or 1.5 times 10 to the 8 kilometers. That is the radius of the Earth's orbit. The Earth is an ellipse, but it's very close to a circle. Okay, so I could just figure out the acceleration. So the acceleration as the Earth goes round and round, I have to take v squared on top, divided by r. I get that number there, 6 times 10 to the minus 6 kilometers squared per second. Now, squared. So if you were to think of it in meters per second squared, it would be down by a factor of 1,000, which is not very much, right? Remember, g is 10 meters per second squared. This is 6,000 of a meter per second. So the acceleration of the Earth going around in this big circle once a year, it isn't very large compared to the acceleration of gravity that we feel on the surface of the Earth. Okay. Man, that is. So the force of gravity, on the one hand, we have the force of gravity. Any force is mass times acceleration. Here the mass is the mass of the Earth. I don't know it. But will I need to know it? Probably not. On the other side, I have Newton's universal law of gravitation. Right? So it has big G. That's a number that we can look up, that we actually had to measure. So I can describe how you measure it if you like. Big M, that's the mass of the sun. That's what we want to get at. Little m is the mass of the Earth. And you can see the mass of the Earth is on both sides. And we have the radius of the distance between the Earth and the sun again a second time. So what we can do is we can rearrange that and just rearrange it to get this expression where we have the acceleration times the distance squared divided by big G. Okay? And we've already calculated the acceleration. Here it is. 6 times 10 to the minus 3. So much smaller than the acceleration on the surface of the Earth due to gravity. But the distance is huge. 2 times 10, that's the square of the distance, right? So it's 1.5 times 10 to the 8 kilometers, which is 1.5 times 10 to the 11 meters, and then I've squared it there. And then G, big G, is the constant of gravity. So that says if I have two masses, 1 kilogram, 1 kilogram, and they're 1 meter apart, that is the force between them in newtons. It's really, 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 really small. But we can measure it, and we did. People started measuring it in the late 1900s. Okay. Oh, I didn't tell you the answer, did I? Maybe we'll do it on the board. So, I have a 6 on the top. This is how we do math in this class, right? I have a 6 on the top, there's a 6 on the bottom. There's some extra little bit on the bottom, and there's some extra little bit with the 2 on the top. So that all cancels out, right? The 6 and the 2 and change, the change with the 2 cancel out the change to the bottom. The 6 on top cancels out the 6 in the bottom. So I'm left with 2 times 10. So I have 22 plus 11 is 33 minus 3. 2 times 10 to the 30 grams. That's the mass of kilograms, rather. So let me write it down. 2 times 10 to the 30 kilograms. So the sun is really, really massive. Right? And we can just figure it out with these few ingredients, right? How fast the Earth goes around the sun, the distance to the sun, and the value of big G, right? So it's a huge number again. Remember what we got for the power was 4 times 10 to the 26 watts. So an interesting question you can ask is the ratio a big number? It isn't really. So if I take the number of watts per kilogram, I take this divided by this, I'll get 2 times 10 to minus 4 watts per kilogram. Do you know how many watts per kilogram one of you makes? Is it bigger or less than the sun, do you think? That's what the sun makes per kilogram. What do you think you do? You make about 1 watt for every kilogram. So, for your mass, you make energy 5,000 times more than the sun, believe it or not. So, how did I get 1 watt? Generally, people put out about 60 watts of energy, something around that. And people weigh about 60 kilograms. Now, maybe you weigh 100 kilograms, you're a big person. Then you probably put out about 100 watts. It's about 1 for a human being. The sun is 2 times 10 to the minus 4. So, I mean, the sun is really big, the sun is really bright, but the ratios of things aren't so unusual, maybe. And maybe we'll focus on those. So let's think a little bit more about gravity, a little bit more about orbits. This is a picture, amazingly enough, from Newton's book. This is from the Principia, this picture. So Newton drew a picture of the Earth. He imagined, let's shoot something off a mountain, and if I give it a little bit of velocity, it'll hit the ground. And a little bit more, point D, it goes a little bit, point E, it goes a little further, F a little further. If you give it enough velocity, what it'll do is it'll just go in an orbit around the Earth, which is what is this curve here, okay? And you could calculate what is the velocity you need to go in orbit around the Earth. And really all you need is what's the acceleration due to gravity on the Earth? 10 meters per second squared. And you need to know the radius of the Earth. And you get 8 kilometers per second. So it's pretty darn fast how fast you need to orbit the Earth compared to what we normally do. So the airplane goes about 1,000 kilometers an hour. So it goes about a little bit less than 300 meters per second, an airplane. So this is a lot faster, right? So 300 meters per second is whatever. 300, this is 30 times that? Am I getting that right in my head? 30 times faster than a plane about to be in orbit. So it's a lot faster. It's also, you have to go a lot faster to go around the Earth. So people talk about these flights where they go into space and they go up to 100 kilometers or something. It takes a lot less energy to go to 100 kilometers above the surface of the Earth than it takes to go in orbit. It's a much bigger feat to go in actual orbit and just go up and fall back. But 8 kilometers per second. Now, and Newton thought about it a little bit more. So if you make the velocity even larger, look at the path letter D, the orbit won't be a circle, it'll be an ellipse. And you can give that projectile more and more velocity, and if you get it up to 11 kilometers per second, then it just leaves. It doesn't come back. Right? Which is always the fear. Like, I go into orbit, but I gave myself 50%, actually about 40% more velocity, I leave forever. Bye-bye. Which is not so good if you want to come home. So if you think about going to the moon, the difference between leaving forever and going to the moon is maybe, this is 11 kilometers a second to leave forever. To make it to the moon might have been 10.8. This is a tiny bit less. So you have to be careful. That's why it's called rocket science. But there you go. So Newton actually realized this. Now, these Newton's laws, they predicted everything in such great detail, but then there were things that just didn't work. And one thing that didn't work is they looked at the orbit of the planet Uranus, which I had a picture of before, and it was just this planet, it was discovered, and maybe they kept watching it for maybe 50 years or a bit longer, and it just didn't seem to follow Kepler's laws very precisely. So what they did is they calculated, well, what's the effect of this planet by all the planets, by Jupiter, by Saturn, those are the most important ones, even by Earth and Venus and everybody. And it still wasn't making sense. And they said something is pulling Uranus along. And they said, this is where we think that object should be. People went and looked, and they found that guy, which is Neptune. So here, people used Newton's laws. They found some discrepancy in their observations. Rather than getting rid of Newton's laws, they said, maybe there's something missing that will be used, that we can use to fix it up. And that missing thing was another planet. Now, we'll learn in the class about dark matter. That's the same sort of idea. We see the sun going around the center of our galaxy, and we ask how fast should it go, but it goes too fast, given what we see. So we think that there's something missing. Not a missing planet in this case, but missing matter. And we call that dark matter. In a certain sense, this planet of Neptune was the first dark matter. And we went out and discovered it. There was this lovely blue ball here. Okay. So there were these discrepancies. People looked at Neptune, right? And they found discrepancies in Neptune. And they went and looked, and they found Pluto. And it turns out they found Pluto. Pluto didn't explain the discrepancies in Neptune, although they thought it did. What it was until we sent a probe around Uranus, we didn't really know its mass very accurately. And now that all makes sense, right? So within the solar system, if we look at Newton's laws, they all make sense with one exception. which is this dude, which is Mercury. And I mean, you can see the same thing in Venus and in Earth and so on. But in Mercury is when it really, it's the largest and was where it was first discovered. So with Mercury, its orbit, we said, orbits are these ellipses, right? In reality, even in Newton's laws, they won't be exactly an ellipse, the orbit of Earth or Mercury. And it's not because even Newton's laws will say they're not an ellipse, because there's the sun, but there's also all the other planets that are pulling on each other. And the fact that there are all those other planets there means that the ellipse won't close precisely, right? Because Jupiter will affect Earth's orbit. Newton's laws say if there's just the sun and a planet, it's an ellipse. But that's not the solar system. It's the sun, a planet, and another planet, and another planet, and another planet, and another planet. But Newton's laws tell you how to calculate the effect of all those other planets. So if you look at Mercury, its orbit doesn't close. It's an ellipse that kind of precesses. It makes a little rosette pattern. And astronomers said, how much does Venus weigh? Which is the big, Venus and Earth are having the biggest effect on Mercury. How much does Venus? What's its mass? What's Earth's mass? What's Mars's mass? What's Jupiter's mass? Added it all up, and they could get away 90% of how, even 95% of how Mercury is tracing this rosette. But they were still left with 5% that they could not explain with Newton's laws. So they said, well, maybe there's another planet, just like with Neptune. It's another planet within the orbit of Mercury, and it's so close that we've not seen it. Well, guess what? It's not there. And what explained what was going on with Mercury was an entire new idea of what gravity is, which is general relativity, which we'll talk about in more detail later in the course. But you have to realize, in the context of the solar system, this correction due to general relativity is really, really small, right? Because if you remember, it's the first guess is it's an ellipse, the orbit. And if you look at that ellipse over 100 years, that ellipse isn't perfect. It's shifted by 1/3 of a degree over 100 years. That's a tiny, tiny, tiny amount. All right? Out of that 1/3 of a degree, 5% of it is due to general relativity. Other 95% is just Newton's laws. So it's a really tiny, tiny thing. But if we look at more extreme objects that we will talk about in the course, or if we look at the entire universe, we have to think about gravity and this idea of general relativity. And don't worry, we will talk about it more. But I'm just putting it in here because we've been talking about gravity.